In this paper, we present an investigation on the feasibility of predicting breakpoints in users' attention away from the keyboard in the input process. During mobile text entry, users tend to shift their gaze from the keyboard to the text entry area to check for errors in the input stream. However, some of the performed checks might be unnecessary, but the user feels compelled to check the input. We examine whether the prediction of breakpoints in users' attention is possible, using a machine learning method that should be lightweight and easy to integrate into the source code of a mobile keyboard. The ability to predict such moments would open up interesting pathways for future research, which might improve the support for text entry with mobile soft keyboards. The process of typing is a complex cognitive process, consisting of three main user-performed sub-tasks, which rely on memory and fine motor control. Firstly, the user has to determine in their mind the desired text to be entered. Then, the appropriate motor functions have to be executed to enter the text. The third, less explicitly discussed sub-task is the need to check the text that has been entered for correctness. This action interrupts the flow of the writing process, which has been found to be detrimental to task performance. We hypothesized that a support mechanism to reduce unnecessary checking behavior might provide users with some cues to continue writing, to prevent shifts of focus away from the keyboard, thus, potentially improving users' typing performance. To develop the model for predicting the breakpoints in users' attention, open gaze and touch data, and open-source processing scripts were utilized. Data was collected for two typing conditions, one-finger typing and two-thumbs typing. Following preprocessing, to proceed with the extraction of the training features, gaze data had to be categorized into records at the text area or at the keyboard area. To achieve this, open-source scripts were utilized, in which two approaches were introduced. The first method was based on a statically defined threshold that divided the mobile screen into two parts, while the second method employed clustering algorithms to detect the change of the user's gaze position. The two methods were applied on all data, and we found that the cluster-based method approximated the true number of gaze shifts better than the threshold-based method. Therefore, we exploited the labeling of the records as obtained by the cluster-based gaze shift detection algorithm. To extract the training features, we processed the gaze data in conjunction with the corresponding keystroke data. The selected features were the last character that has been pressed, the number of characters typed since the last time space was pressed, the number of lower gaze points that have elapsed since the last time an upper gaze occurred, the time elapsed from the last upper gaze to the current gaze event, and the number of characters typed since the last upper gaze. Following feature extraction, for the one-finger typing condition 95.4% of the gaze events were labeled as a lower gaze and 4.6% as an upper gaze. For two-thumbs typing, 89.7% of the gazes were labeled as lower gazes, and 10.3% as upper gazes. For each typing condition, an SVM was trained following two approaches, a 10-fold cross-validation approach and a leave one person out approach, using data from 29 participants for training, and the data of the remaining participant for testing. Adopting the 10-fold cross-validation approach, model performance was surprisingly good across all metrics. Due to class imbalance, we paid particular attention to the macro F1 score and macro recall. Macro F1 score improves slightly in two-thumbs typing, while macro recall is considerably lower in one-finger typing. In general, the model exhibited improved performance in two-thumbs typing. Model performance remains good for the second approach, while exhibiting improved performance in the two-thumbs typing condition, corroborating the results of the first training approach. For the leave one person out approach, we also present the ROC curves, where we can observe that the results are, for all users, better than random, but for some users, the features and model built by them seem to work better than for others. Building on previous work, we found that the prediction of breakpoints in users' attention can be approximated with encouraging results by our proposed model, even in the case where no behavioral information is known about a particular user. We selected SVM as a classifier that could be integrated in a mobile keyboard, as literature supports the suitability of SVMs for binary classification, speed of inference on mobile devices and low power consumption. Our work faces constraints in generalizing findings due to the source and experimental settings of the open datasets. To address this, we plan to conduct further investigation in real-life settings and alternative evaluation methods. Additionally, we aim to explore models that do not rely on eye tracking data, utilizing only mobile device extracted data. In our paper, a machine learning model yielding encouraging results in predicting users' gaze shifts away from the keyboard was introduced. Our findings can facilitate further research in integrating lightweight machine learning models into the source code of a mobile keyboard, aiming to improve users' typing efficiency.